Introduction. Today, Tanuj came to the market with his father for shopping. He wants to buy some t-shirts and trousers. He enters a shop and saw a variety of colorful t-shirts. Father, there are so many different colors of t-shirts, and I like the blue one. Okay, son, then we must purchase it. Thanks, father. Son, do you know how these colors are applied on the clothes? No, father, but I wanna know. Different colors are obtained by applying specific chemicals for specific color on the clothes. These chemicals are the coordination compounds. Coordination compounds? What are these? I don't have any idea about this, and I want to know about the coordination compounds. Students, today we will study more about the coordination compounds. Objectives. At the end of this lesson, you will be able to define coordination compounds, explain Werner's theory, define basic terminologies, differentiate between double salt and complex compound, understand nomenclature of coordination compounds, describe isomerism in coordination compounds, explain valence bond theory and crystal field theory, know about bonding in metal carbonyls, analyze stability of coordination compound. Definition. The branch of inorganic chemistry that deals with the study of coordination compounds is known as coordination chemistry. A coordination compound contains a central metal atom which is surrounded by a suitable number of neutral molecules and usually retains its identity in solutions as well as in solid state. These compounds are widely present in minerals and plants. They have many real-life applications like estimation of hardness in water, soil and plant treatment, electroplating and textile dyeing. Werner's theory. In 1893, Alfred Werner successfully explained the properties of coordination compounds in terms of their structure. The brief outlines of his theory are following. Metals have two types of linkages, primary and secondary linkages. The primary linkages are satisfied by the negative ions, whereas the secondary linkages may be satisfied either by the negative ions or by neutral molecules. The primary valencies are ionizable valencies, whereas the secondary valencies are non-ionizable valencies. Each metal atom can have a characteristic number of secondary valencies about the central atom. These valencies are projected in the space about the central atom in such a manner that these assign a definite geometry to the coordination compound. Not only the neutral molecules are coordinated to the central atom, but ions may also be coordinated in same fashion. When an ion replaces a neutral molecule in the coordination sphere, it loses its electrovalent character and gets attached to the central ion by non-ionizable linkage. Coordination entity. A complex ion is an electrically charged radical or species carrying positive or negative charge in which the central atom or ion is surrounded by a suitable number of neutral molecules or negative ions. For example, CONH3 4Cl2. The complex ion carrying a positive charge is called cationic complex. For example, NiNH3 6 2 positive. The complex ion carrying a negative charge is called anionic complex. For example, PtCl6 2 negative. The complex ion carrying no charge is called neutral complex. For example, NiCO4. Ligands. The neutral molecules or ions that surround the metal ion in a complex are known as ligands. Ligands are normally polar molecules which have at least one unshared pair of valence electrons. They get attached to the central metal ion by a coordinate bond. The atom in the ligand which is involved in the formation of coordinate bond with central metal atom is called coordinating atom or donor atom. A ligand may contain one or more donor sites. Depending upon the number of donor sites, the ligands are of following types. Unidentate with one donor site, for example, carbonate ion. Bidentate with two donor sites, for example, oxalate ion. Tridentate with three donor sites, for example, triethylene triamine. Tetradentate with four donor sites, for example, triethylene tetraamine. Hexadentate with six donor sites, for example, ethylenediamine tetraacetate ion. An atom can have only one donor site, but a molecule can have more than one donor sites. Denticity and chelation. When a multidentate ligand simultaneously coordinates to a metal ion by more than one donor site, then a ring-like structure is obtained. This ring-like structure is called a chelate ring. Pt trion 2 positive is an example of chelation. The ligand coordinates to a metal ion to form a ring-like structure is known as chelating ligand. The number of such ligating groups indicates the denticity of the ligand. A didentate ligand is symmetrical if the two coordinating atoms are the same. If the two coordinating atoms are different, it is unsymmetrical. Some properties of ligands. Inner metallic complexes. When ligands possess both neutral and anionic groups, coordinate with metallic cation, they form complexes in which both the coordination number and charge of the cation are satisfied simultaneously. Flexidentate character. A polydentate ligand may not necessarily use all its donor atoms to get coordinated to the metal ion. For example, EDTA can act as a hexadentate or a pentadentate or a tetradentate ligand. Ambidentate ligands. Some unidentate ligands have more than one donor atoms through which they can coordinate to the central atom. Coordination sphere and coordination number. Coordination sphere. In the complexes, the central metal ion along with the non-ionizable ligands attached to it is called coordination sphere. The portion present outside the square brackets is called ionization sphere. Species present in the coordination sphere are non-ionizable. Species present in the ionization sphere are ionizable. Coordination number. The total number of ligands attached to the central metal atom in the coordination sphere is called coordination number of the metal atom. Coordination polyhedron. In the coordination sphere, ligands attached to the central atom lie in space in definite directions. It gives a definite geometry to the complex ion. This spatial arrangement of ligand atoms which are directly attached to the central atom is called coordination polyhedron about the central atom. The commonly observed polyhedra are square planar, tetrahedral, trigonal bipyramidal, square pyramidal, octahedral. For example, square planar polyhedra observed in PtCl4 2 negative, tetrahedral polyhedra observed in NiCO4, and octahedral polyhedra observed in CONH3 6 3 positive. Oxidation number of central atom. The oxidation number is the residual charge that appears on the central atom when all other atoms are removed from it. The charge on a complex is the sum of the charges of the constituent parts. The sum of charges of the constituents is equal to 0 if the complex is neutral. The sum of charges of the constituents is equal to the charge on the coordination sphere for an anionic or cationic complex. The total electrovalent charge on the complex ion changes with the number of charged ions which may enter into coordination sphere to replace neutral molecules. Effective atomic number EAN. Effective atomic number of the central metal atom in a complex can be easily calculated by using given formula. EAN is equal to Z minus ON plus 2CN, where Z is the atomic number of the central metal atom, ON is the oxidation number of the central metal atom, and Cn is the coordination number of the central metal atom. A stable complex is formed if the EAN is equal to the atomic number of the next noble gas. For example, EAN of FeCO5 is equal to 26 minus 0 plus 2 into 5 is equal to 36. EAN rule is applicable in most of the cases. Complexes of Ni2, CO2, Ag1 generally do not follow this rule. Fe in FeCl4 minus 1 and FeCN6 3 minus never follows this rule. Homoleptic and heteroleptic complexes. Homoleptic complex. The complex in which metal ion is coordinate bonded to only kind of ligand. The term uses a homo prefix to indicate that something is the same for all. For example, CONH3 6 3 positive and FeCN6 4 negative. Heteroleptic complex. The complex in which metal ion coordinate bonded to more than one kind of ligands. It is possible for some ligands to bind with two or more different coordination modes. For example, COCl2 NH3 4 positive. Difference between double salt and complex compound. Let's make some important differences between double salt and complex compound. Double salts do not have coordinate bonds, whereas complex compounds have coordinate bonds. Double salts exist in solid state, whereas complex compounds exist in solid state as well as in aqueous solutions. Double salts lose their identity in aqueous solution, whereas complex compounds do not lose their identity in aqueous solution. Double salts contain two salts in equimolar ratio, whereas complex compounds contain ions which may or may not be in equimolar ratio. In double salt, metal ions show their normal valencies, whereas in complex salts, metal ions show primary valencies and secondary valencies. Double salts form simple ions in aqueous solution, whereas complex compounds form complex ions in aqueous solution. Nomenclature of coordination compounds. Coordination compounds and complexes are formulated and named in accordance with the rules suggested by Inorganic Nomenclature Committee of International Union of Pure and Applied Chemistry. Rule 1. Cation is named first, followed by anion. Rule 2. Species present in coordination sphere are written in one word. Rule 3. The ligands are written in alphabetical order and their number is indicated by di, tri, tetra, etc. Rule 4. H2O is named aqua, NH3 as amine, NH2 as amine, and anionic ligands end in O. Rule 5. Anionic complex ends in ate. There is no change in case of neutral and cationic complexes. Rule 6. The oxidation state of the central metal is indicated by Roman number in brackets. Naming of polynuclear coordination compounds. If the complex contains two or more metal atoms, it is called polynuclear complex, and the ligands binding the two metal atoms simultaneously are called bridging ligands. In naming such ligands, the alphabet mu is written before the name of such ligands and is separated from the rest of the complex by hyphens. For example, this coordination compound is named as tetraamine cobalt 3 mu amido mu nitro tetraamine cobalt 3 nitrate. Example on nomenclature of coordination compounds. Let's take an example on nomenclature of coordination compounds. What is the name of coordination compound CrH2O4Cl2Cl? Let's see the solution. In the formula of coordination compound, the complex is written first, therefore it is cationic complex and it should be named first. As per rules, while naming the complex, ligands are written first followed by the name of central metal ion. Ligands are to be written in the alphabetical order, so aqua comes first and chloro afterwards. The oxidation number of central metal atom is +3 and is written in the parentheses in Roman numerals. The anion is chloride. Hence, the name of this coordination compound is tetraquadichlorochromium 3 chloride. Write formula of a coordination compound. When the name of a coordination compound is given, then some rules are to be followed for writing its formula. Rule 1. The formula of the cation is written first, followed by that of the anion. Rule 2. The coordination sphere is written within square brackets. Rule 3. The sequence of symbols within the coordination sphere is that the central metal should be represented first, followed by the ligands in their alphabetical order. Rule 4. The formula of a polyatomic ligand is enclosed in parentheses. Rule 5. There should be no space between ligands and the central metal atom within the coordination sphere. Rule 6. In a coordination compound, the charge on cation is balanced by charge on anion. Isomerism in coordination compounds. The two or more chemical compounds with identical chemical formula but different structures are called isomers, and the phenomena is known as isomerism. In coordination compounds, the ligands are arranged spatially in specific orientation around a given metal atom. Several isomeric possibilities arise depending upon the position and arrangement of ligands around the metal ion. Isomers can be broadly classified into two major categories: structural isomers and stereoisomers. Structural isomers. Structural isomers have different arrangement of ligands around the central metal atom. The various types of structural isomers are following. Linkage isomerism. It occurs when the ligand is ambidentate and can combine from two or more different atoms. Coordination isomerism. It is shown by complexes when both cation and anion are complexes and the metal ions are interchanged between them. Ionization isomerism. This is due to the exchange of groups between complex ion in coordination sphere and the ions outside it. These isomers give different ions in solution although they have the same chemical formula. Hydrate isomerism. This arises because of the capability of solvent, normally water molecules, to appear in a variety of ways, inside and outside the coordination sphere, to give a number of isomers. Stereoisomers. Stereoisomerism is due to different arrangement of atoms or groups in space. These are of two different types. Geometrical isomerism. This type of isomerism arises in heteroleptic complexes due to different possible geometric arrangements of the ligands. When two identical ligands occupy adjacent positions, the isomer is called cis isomer. When two ligands are arranged opposite to one another, the isomer is called trans isomer. Four coordinate complexes of type Ma2b2 and 6 coordinate complexes of type Ma4b2 shows geometrical isomerism. Optical isomerism. Optical isomerism is due to the presence of non-superimposable mirror images. The non-superimposable mirror images are called enantiomers. The enantiomers react differently with the plane polarized light. The enantiomer which rotates the plane polarized light in a clockwise direction is called dextrorotatory, and the enantiomer which rotates the plane polarized light in anti-clockwise direction is called levorotatory. 6 coordinate complex containing 3 didentate ligands shows only optical isomerism. Valence bond theory. The basic principles involved in the valence bond theory are hybridization of orbitals, bonding between ligands and the metal atoms, relation between the observed magnetic moment and the bond type. According to this theory, ligands bonded with central metallic atom by a coordinate covalent bond. Therefore, ligands must have a lone pair of electrons and the metal must have some empty orbitals available for bonding. For example, the formation of K4MnCN6 can be explained on the basis of valence bond theory. Outer orbital complex. The complex in which d orbitals of outermost orbit are used for bonding are called outer orbital complex. Inner orbital complex. The complex in which d orbitals of inner orbit are used for bonding are called inner orbital complex. High spin complex. The complex which contains maximum number of unpaired electrons in a particular electronic configuration known as high spin complex. Limitations of valence bond theory. The main limitations of valence bond theory are following. It does not explain the color exhibited by coordination compounds. It does not distinguish between weak and strong ligands. It involves a number of assumptions. It does not make exact predictions regarding the tetrahedral and square planar structures of 4-coordinate complexes. It does not give quantitative interpretation of magnetic data and thermodynamic stability of coordinate compound. Crystal field theory. The important points of the crystal field theory are following. The attraction between the central metallic atom and ligands in the complex are negligible. The central metallic atom in the complex is regarded as a positive ion of charge equal to the oxidation state. There is a repulsion force between electron on central metal and ligands. Thus, the electrons occupy the d orbitals farthest away from the direction of approach of ligands. Ligands are considered as a point charge. In the formation of complex, d orbitals are split into the different energy levels. The main limitations of crystal field theory are following. The assumption that ligands are point charges is not practically true because anionic ligands should have strong field, but actually many of them are not. It does not take into account the covalent character of bonding between the ligand and the central atom. Crystal field splitting of d orbitals. The 5 d orbitals can be classified into 2 sets. 3 of d orbitals which are oriented in between the coordinate axes are called T2g orbitals. The other 2 d orbitals oriented along the axis are called Eg orbitals. In the case of free metal ions, all the 5 d orbitals have equal energy, but their interactions form one pair of ligands and their energies also become deficit. This splitting of 5 d orbitals of metal ions under the influence of approaching ligands is called crystal field splitting. It is denoted by delta and is called crystal field splitting energy. The ligands which cause greater crystal field splitting are termed as strong ligands, while those which cause lesser crystal field splitting are weak ligands. Crystal field splitting in octahedral and tetrahedral complexes. In octahedral complexes, the 6 ligands approach the central metal ion along the coordinate axis is the axis dx2-y2 and dz2 orbitals. The set of orbitals has higher energy than T2g of orbitals. In tetrahedral complex, 4 ligands may be imagined to occupy the alternate corners of the cube and the center ion at the center of the cube. In this situation, the T2g set of orbital lie relatively nearer to the approaching ligands and therefore T2g set of d orbitals have higher energy than Eg set of orbitals. The relationship between delta T and delta O is given by delta T is equal to 4 by 9 delta O. Color in coordination compounds. The color of complexes is due to absorption of light in visible region of spectrum and radiation of complementary color. The energy is absorbed by electrons present in d orbitals and they get excited to higher energy d orbitals from lower energy d orbitals. They radiate energy when they come back to lower energy d orbitals. The colors of coordination compounds of transition metals are fascinating. In aqueous solution, colors are observed due to presence of aqua complexes. The color changes even with change in coordination number and nature of ligands. The color changes with change in oxidation state. Bonding in metal carbonyls. The homolyptic carbonyls contain only carbonyl ligands and are formed by most of the transition metals. Important metal carbonyls are formed by the metal from the central part of the D block. Bonding in metal carbonyl involves both sigma and pi bonds. Sigma bond is formed by overlapping of lone pair on carbon monoxide with the vacant d orbital of transition metal. Pi bond is formed by back donation of pair of d electrons to vacant anti-bonding orbital of carbon monoxide. Properties of metal carbonyls. Some important properties of metal carbonyls are following. Mononuclear carbonyls are either colorless or light colored. Polynuclear carbonyls are more deeply colored. Metal carbonyls are mostly solids at room temperature and pressure except iron and nickel carbonyls, which are liquids. They are highly reactive due to metal center and the CO ligands. The mononuclear carbonyls are volatile and toxic. Most of metal carbonyls are soluble in hydrocarbon solvents. Metal carbonyls are used as industrial catalysts and as precursors in organic synthesis. Stability of coordination compound. The formation of complex involves reaction between a metal ion and ligands. If the force of attraction between central metal ion and ligands is strong, complex will be stable. The stability of complex depends upon nature of ligands, nature of metal ion, pH of solution and temperature. The formation of complex in a solution is a reversible reaction and is exothermic process. The equilibrium constant K is called stability constant. Higher the value of stability constant, more stable will be the complex. Smaller the cation, greater the charge on it, more stable will be the complex. Stronger the ligand, more stable will be the complex. Applications of coordination compounds. Some important applications of coordination compounds are following. Bauxite is purified by forming complex with NaOH. EDTA is used for estimation of Ca2 plus and Mg2 plus in hard water. EDTA is used to remove Pb forming Pb-EDTA complex, which is eliminated in urine. Hemoglobin contains Fe, chlorophyll contains Mg, and vitamin B12 contains CO2+. Cisplatin is used as anti-tumor agent in treatment of cancer. They are used in photography. Silver and gold are extracted by treating zinc with their cyanide complexes. Did you know? Coordination compounds are used in electroplating. In 1893, Alfred Werner proposed a theory to understand the difference between coordinated and ionic in a compound. Isomers have the same number of atoms of each element in them and the same atomic weight but differ in other properties. Summary. Let us summarize what we have learned. A coordination compound contains a central metal atom which is surrounded by a suitable number of neutral molecules and usually retains its identity in solutions as well as in solid state. The primary linkages are satisfied by the negative ions, whereas the secondary linkages may be satisfied either by the negative ions or by neutral molecules. The neutral molecules or ions that surround the metal ion in a complex are known as ligands. The ligand coordinates to a metal ion to form a ring-like structure is known as chelating ligand. The total number of ligands attached to the central metal atom in the coordination sphere is called coordination number of the metal atom. Structural isomers have different arrangement of ligands around the central metal atom. Stereoisomerism is due to different arrangement of atoms or groups in space. The complex, which contains maximum number of unpaired electrons in a particular electronic configuration, is known as high-spin complex. Important metal carbonyls are formed by the metal from the central part of the d block.